Let's look at question 6 now from your revision sheet, external and internal flows. In particular, this question looks at internal flows. We are told that a light aircraft weighs 10 kilonewtons, the weight of the pilot and passengers 5 kilonewtons, and you're given a specific aerofoil number, NACA 23012. Remember that the new name for NACA, the organization that certifies and standardizes aerofoil names and dimensions, is called NASA. So NACA is the old name for NASA, National Aeronautics Space Administration. You're told that this aerofoil has a chord length of 1.8 meters and a wingspan of 25.6 meters, and for this light aircraft there are no flaps. You are asked question A, what is meant by the statement the takeoff speed at a 5-degree angle of attack at sea level? What does it mean? So let's look at how we might answer this. If we look at the first answer, an aircraft will take off when the lift equals the total weight of the aircraft and its payload. An angle of attack, the lift coefficient CL 0.6, the data is read from the NACA 23012 aerofoil data sheet. So let's go back and look at that aerofoil sheet. Now I have highlighted the details. Angle of attack 5 degrees, no flaps. So we use this line, and the lift coefficient is 0.6. You are asked to determine the takeoff speed of the aircraft at 5 degrees angle of attack. Okay, let's look at how we solve this. When we know that at takeoff the weight of the aircraft is equal to the lift force, we substitute the lift force for half times the lift coefficient times the density of the air times the takeoff speed times the planform area of the aerofoil, and we make V the subject of the formula, and we get this expression. What we do next is we substitute the values in the sum, and we get a value of 29.8 meters per second, or 107 kilometers an hour, since 1 meter per second is equal to 3.6 kilometers an hour. That's quite simple and straightforward. Now let's look at the third part. Calculate the stall speed of the aircraft. Now, some of you have spoken to me concerning the next point here. Are we supposed to bring the entire printed book into the exam? Now, this question might have been taken from previous years where there's no electronic book available at that time or given. Now that you have an electronic book, the questions have been crafted to allow you to get as much information as possible from the question. And where any data sheets are required, you will be told before the exam what are the relevant data sheets, if necessary, to bring them. Okay, so in this case, we are supposed to calculate the stall speed for the aircraft. Now, if we go up, first we define what is stall. the decrease of lift with an increase of the angle of attack is called stall. When the flow separates over nearly the upper half of the aerofoil, the lift dramatically is reduced. The separation point is the separation between the fluid stream and the geometry of the aircraft at the leading edge. Okay, how do we calculate the stall velocity? Using the maximum lift coefficient in the equation in star. Okay, so if we go to our equation above, we are using this formula, substitute our values, and we can find our velocity 18.7 meters per second. And this is when you have the maximum lift. Let's go back to our aerofoil data. If you look at the question, maximum lift, okay, occurs at the point indicated. All we need to do is we substituted that value, because at that point you notice the lift begins to dramatically fall. Okay, in fact there is no data after this. This is the point at which stall begins to occur. So all we need to do is use this 1.52, substitute in, and we will get, this is the stall speed of the aircraft. Now, it would be wise at this stage for you to revise your PowerPoint slides, which we did together, on the various terms. Now, you notice here we have talked about lift and we have talked about stall. Please also use the opportunity to revise some of the things that I mentioned. In particular, these terms are pretty important in aircraft technology. Induced drag. Okay, these pictures are all extracted from your PowerPoint slides. Okay, you don't have to copy it. I'm just alerting you. It's not given in the solution because all that you see here is from your PowerPoint slides. All what I did was cut and paste. In fact, there are more details in your PowerPoint slide. Induced drag, it says here from the notes, tip vortices that interact with the free stream imposes forces on the wing tips in all directions, including the flow direction. The component of the force in the flow direction adds drag, and this is called induced drag. The other term, aspect ratio, the ratio of the square of the average span of the aerofoil to the planform area. Remember, for an aerofoil, the planform area is the wingspan multiplied by the chord length. So for an aerofoil with a rectangular planform, chord C and span B, the aspect ratio is the square of B over A, which makes it B over C, where the planform area is B times C. The aspect ratio is a term that is used to measure how narrow the airfoil is in the flow direction. So please go through your PowerPoint slides again for the exam for the external flow. There's quite a bit of material, but if you revise through it at least once or twice, you should be able to acquit yourself well for the exam. So all the best for the exam. We will take discussions after this series of tutorial revisions. So please ask as many questions that you have that is in fact or that are troubling you. Thank you.